welcome back after the short break. Before the break we are talking about the model of voltage amplifier, and as I have given a hint that the amplifier need not be always voltage amplifier. They are maybe based on the signal at the input and signal at the output, we may be having different types of amplifiers. So, let us talk about other kind of amplifier called current amplifier, and whenever we are talking about current amplifier similar to voltage amplifier, what does it mean is that it is an equivalent linear circuit which provides dependency of the output signal, output current signal on the input current signal. So, note that the output signal and input signal both are current, and that is why we call this is current amplifier. So, similar to the previous case, here we do have one example having this is also amplifier having one BJT, and as you can see here what are the things we do have is the BJT is at the central place, and then it is having a DC bias through the RC. We are giving proper voltage at the collector of the transistor, and then we do have a DC current at the base, which is providing a meaningful bias to the base of the transistor. Either you can think of this VB, it is setting the VB or the DC base current, but whatever it is, this is also providing one bias in condition, and depending on this IB and beta of the transistor, we may be having a if the device it is in active region of operation, we may be having this collector current, DC collector current. So, this DC collector current is flowing through this RC, providing a voltage drop, and most likely that even after deducting this drop, the VCC it is sufficiently high, so that its base to collector junction it is reverse bias, namely keeping the device it is in active region of operation. So, there is the main part here. So, the main part it is here including the bias and all, and then if we feed the signal in the form of current at the base as you are seeing here, and depending on the current here, we are expecting this current it will be flowing. Note that in simplistic model here we are showing this is signal current, which means that its average it is 0 and need not be sinusoidal, but sinusoidal things we may consider as one special case. So, at the base of the transistor, what you can say that the base current to the transistor it is having two components, namely the capital I capital B, the DC part, and also the time varying part which is shown here. So, it is having a DC part here and the time varying part. So, the time varying part is given here. So, these two together they are giving the total base current. So, as a result the current flowing through the collector it is also having two components, one is the DC part and the small signal part. Now, if you are observing the voltage at the collector without making any connection here, then you may see the voltage is changing there. But in case if we are looking for this circuit as a current amplifier, then at the output we like to extract this signal in the form of current. So, what we do? We like to short this output node to ground, and then we like to extract the entire signal. But while we are doing this, we have to make sure that the output node it is not really or rather the collector node it should not get shorted to DC ground, and hence we need to put one DC blocking capacitor, or it is referred as AC coupling capacitor. So, for time varying signal, whether it is current or voltage whatever you say, that we can think of this capacitor is essentially working as a short. So, the current, whatever the current we will be observing here is the variable part of this the collector current. So, we may call this is a small I small out. So, the collector current here we can see the total current here, it is having a DC part. So, it is having a DC part here, sorry, it is having a DC part here. So, the DC part it is capital I capital C, and then it is having the, on top of that it is having the small signal part. Okay. So, in case if we are not connecting anything here, actually this IC it will be flowing here, or small I out will be flowing here, but you, in case if you want to extract the signal, you need to connect to AC ground through this capacitor to extract this entire current. So, naturally the voltage here ideally by making this connection it will not change, and then you can say that whatever the current it is flowing, the signal current it is flowing, it will not flow through this resistor. So, the current whatever we obtain here, which is referred as the short circuit current, or it is called unloaded current. I must say it is unloaded current, since the signal here it is current form. So, to get the entire current you must short this to AC ground to extract the entire current. For voltage signal we like to keep the output node open, whereas for current signal at the output node we must sort it to AC ground. So, anyway, so this is what the amplifier, overall amplifier, as I said that at the input we are giving say DC current here and along with the signal current, and at the output what we obtain here it is a DC part and a small signal part. But then whenever we like to see this circuit as an amplifier or the signal amplifier, then our main focus is that this is the input and this is the corresponding output. So, whenever you are talking about the model of the current amplifier similar to voltage amplifier, what we are looking for, it is simplified equivalent circuit which must represents this entire circuit in terms of finding the relationship between this final output to this input. Okay. So, what we have said here, let me again summarize in the next slide. I think I do have the next slide to summarize. Yes. So, whenever we are talking about the model of amplifier, so what we are referring to, it is so we are basically referring to one equivalent linearized circuit which is representing the entire circuit to find the input to output relationship, So, what may be the corresponding circuit here, that is what we are going to say it is the model of the amplifier. So, similar to the voltage amplifier, here again we like to remove the DC part, we like to exclude the DC part and the model to simplify the circuit. So, we will be definitely excluding this part, and also to avoid the DC current, we are I should say that we are feeding the signal only through coupling capacitor. Likewise, while we are extracting the signal, we are putting a DC blocking capacitor here at the output port. So, we are assuming that these arrangements are there. So, for in the model, however, since we are focusing on the signal which is having sufficiently high frequency, for which this capacitor it is working as a short, this is also working as a short. So, this, as I said, that this DC part need to be made 0. So, likewise the DC part we are making it 0 by putting this capacitor. Now, to again to see what are the basic elements are there in the current amplifier, let me focus on let me start with a fresh slide. So, what we are going to do in the current amplifier model, it is we like to get the relationship between the primary input called the source current to the primary output. And the model, whatever the model we are going to discuss here, it must be having input to output current gain, and it should be unloaded current gain. So, the first element of the model, we are expecting that we must be having a current dependent current source. So, if I say that the gain of this amplifier, it is say A I. So, the output current, unloaded current should be A I times the input current I in. So, that is the current here, which is the unloaded current. And then similar to the voltage amplifier, and what is I in is whatever the current is entering to the circuit, So, the circuit may be having element like, say, having one element which is having some finite conductance or finite input resistance, but whatever it is, as long as I in is entering here, and then we are getting the corresponding output here, and the output it is in the form of current. Now, this element A I, as I said, this is the first parameter or first element of this model. The other two elements supposed to capture the loading effect at the output port and input port. Now, the moment we connect a load at the output instead of directly shorting it. So, if I am having a finite resistance at the output, so it is expected that practically the current flowing through this circuit may not be same as the internal current. So, whatever the current we will be seeing here called I out need not be the total current what we are getting here. In other words, the we must add one non-zero conductance to this element in parallel with this current dependent current source. So, either you may say that this conductance is G naught, or you can write in terms of resistance called R naught, and the output port of course, it is here. So, the moment we connect this R L, obviously, then the total current it will be getting bifurcated. One part it will be flowing through this R L, another part it will be flowing through this R O. So, these two currents, so this current and this I out together it is giving the internal current, which is of course, it is what we call it is unloaded current. When I say unloaded current, which means that R L is equal to 0. If I make this R L equal to 0 for a finite value of R O, then we can say that the current flowing here it will be same as this one, because the drop across this resistance, if this is 0, then this is 0. So, the drop across this R O it is 0. So, the current here it will be 0. So, then I out it will be entirely same as the internal current A I multiplied by I in. So, again what I said is that this R O represents the practical loading effect in the circuit. So, if we are having load resistance R L which is non-zero, then whatever the reduced current we will be seeing, that reduced current it will be again it can be calculated by considering this R out. So, same thing at the input side, the input resistance, ideally we want this input resistance to be 0, but practically when you consider a circuit and if we are stimulating this circuit by a signal current so if I say that this is I s and if I directly feed this current to the circuit, the internal current I in or the current going to the circuit need not be same as this I s, so which means that along with this I s, practically if it is having some conductance, and this conductance either we can call it is G s, the source conductance, or we can write in terms of resistance say R s, and the moment we connect it here, it is not that entire current it will be flowing here. That is because this R in practically it is non-zero. So, the moment I connect practical value of R in or non-zero value of this R in, the current I in it is coming to the circuit, it will be only a fraction of this I s. Of course, depending on the relative value of this R s and R in, this I in it will be a significant part or maybe small part of it, but whatever it is, this I in it is producing the internal current A I times I in. So, what we have seen here, again I am showing in different slide to summarize whatever we have discussed about the model. So, the current amplifier model, it is shown here by this dotted line. So, this is what the current amplifier model. So, this is the model of the current amplifier. And then as I said that it is having three important parameters, namely the unloaded current gain A I, which gives the internal output current after multiplying with I in, and then other element is that R o, which is representing the loading effect at the output port, and then R in, which is representing the loading effect of the circuit whenever we do have this non-zero conductance, namely R s if it is finite, then whatever the bifurcation it will be happening, that will be getting represented by this R in. So, if you look into say this input port, the I in, it is as I said that it will be, so we can write that I in equals to, so whatever the I s we do have multiplied by this parallel resistance, it is developing the voltage, divided by R in is the current, or simply you can say that R s divided by R in plus R s. So, we can say at the input we do have the loading effect getting captured by this R in. So, likewise at the output, whenever we are talking about the output port, at the output port we do have the output current I out, it will be internal unloaded voltage E I times I in multiplied by R o divided by R o plus R L. So, again, so these two important equations, they are representing the loading effect. So, by considering these two loading effects along with this E I, you can find what will be this I out and I s relationship. In case if we have a circuit which is having multiple stages, each of the stages if you can break into as a current amplifier, then each of these amplifier stages you can model by this circuit. So, you can have say one current amplifier followed by another current amplifier, and then maybe the primary input and primary output. So, the output port parameter of the first stage along with the input port parameter of the next stage together, again it will be producing one loading effect. So, everywhere wherever we are making connection from one stage to another stage, or maybe feeding the signal, or you are connecting the load, everywhere you will be having the loading effect. And this R in and R O, they are playing important role to capture this loading effect. So, that is about the current amplifier. So, as we said that we have discussed about voltage amplifier, and then also we have discussed about the current amplifier, and you might have seen that whenever you are talking about say current amplifier, the signal here it is current, and the signal here it is current. But there may be a practical situation where we cannot say that signal always be of same nature. In case say input is say current and output is voltage, then what kind of model we will be using, or say if the input is voltage and output is current, then what kind of model we will be using. So, based on the signal type here, if it is voltage and then current, we will be having one kind of amplifier or third kind of amplifier, and likewise if I am having the input is input signal is current and then output signal it is in the voltage form, then we will be having the fourth kind of amplifier. So, utilizing this this port nature, namely if the signal here it is current, we are representing this the output port in the form of Norton equivalent circuit. On the other hand, if it is voltage, then we are representing this by Thevenin equivalent circuit. So, depending on this signal type, either we can have the Norton equivalent or Thevenin equivalent, but then depending on the signal here, the controlling elements, it may be current or voltage. So, based on whether it is current or voltage, we can have different parameters here. So, let us see that the other two types of the amplifiers and their corresponding model. So, suppose you do have this situation like this. At the input you do have the signal in the form of voltage, and then at the output you do have the signal in the form of current. So, as the signal at the output it is current, so we are expecting that in the model it should be Norton equivalent, isn't it? So, we will be having a current source, but then it will not be current dependent current source, because the signal here it is voltage, rather it will be voltage dependent current source. So, since it is relating the input voltage to output current, so we call this is conductance, and it is representing mutual relationship from input port to output port. So, we denote this parameter by capital G M, called trans-conductance, then multiplied by of course, the corresponding signal. So, what is the signal? It will be V in. V in is the signal appearing at the input port of the circuit. So, we may call this is V in, and the V in is basically the input port voltage. And so, since it is Norton equivalent, to take care of the loading effect, as you might have seen for the current amplifier, we like to put one finite conducting element, and its conductance you may write in terms of G conductance, or you can, for simplicity, you can write the resistance R naught. and at the input again to take care of the loading effect at the input port, we may have a finite input resistance. So, note that if this R in is higher, it is better in case if the signal it is in voltage. Anyway, we do have these three elements. One is the transconductance of this amplifier, output resistance, and then input resistance. And of course, at the input, so we are feeding the signal in the form of voltage, and this voltage source may be having its finite resistance called the source resistance R s, and this is of course, the V s. And here again you can see that R s and R in together it will be creating a potential division of V s to produce this V in. So, likewise at the output side, in case if we are connecting a load here instead of directly shorting to ground to see the corresponding signal output. So, the I out here, it will not be entirely this internal current, instead there will be some potential division. So, there will be a potential division or rather I should not say potential, current division between this R o and R l. So, here in this case we can say that I out it will be G m times V in multiplied by R o divided by R o plus R l. So, this is again taking care of the loading effect. So, likewise at the input side the V in it will be V s multiplied by R in divided by R s plus R in. So, here again we do have the this factor to take care of the loading effect. Now, if I combine these two equations, we can find the relationship between this the I out and the V s. So, we can say that I out it will be, let me use this space, I out it will be okay. So, if I replace this part by its expression in terms of V s. So, I do have R in divided by R s plus R in into V s. So, that gives us the overall gain of the circuit, capturing the loading effect at both the ports. So, likewise if the signal it is at the input port it is say current, if this is current and this is voltage, then we can again model the circuit differently of course, but since the output it will be voltage, then the output port it will be Thevenin equivalent. So, let us see that model in the next slide. So, here as I said that the output it is voltage. So, the output port it will be the Thevenin equivalent. So, we do have Thevenin equivalent. This is dependent voltage source and also it is having Thevenin equivalent resistance called R o, and this dependent voltage source it depends on the current. So, what we write here the parameter it is actually it is impedance, and since it is correlating the output port to input port, we call Z m mutual impedance, or it is called trans-impedance, and this trans-impedance multiplied by the whatever the current it will be having at the input port. So, I in times Z m, it produces a voltage here which is referred as the unloaded internal voltage, and at the input again to take care of the loading effect, we are having finite resistance called R in. And in case if we are connecting say a load at the output, say R L, the voltage here it will be reduced version of this voltage. So, likewise at the input of course, it is current source. So, we will be having a signal current here say I s, and it is having a finite conductance say R s. So, again this R s and R in, they are providing the loading effect at the input port, and then R o it is along with this R L, finite value of R L, it is providing the loading effect at the output port. So, the model of what we are seeing here, basically this part is the trans-impedance model of the trans-impedance amplifier. So, now we are having 4 basic models or of different types of amplifiers based on the signal type. So, if we are having one amplifier having multiple stages, and these stages need not be only one type of amplifier. Say for example, this is a voltage amplifier, okay. And then we do have say trans-conductance amplifier, okay. And then you may be having say current amplifier, okay. And then we may have say trans-impedance amplifier. Note that while you are connecting it, the signals are consistent. So, if you see here, since it is voltage amplifier, it produces a signal here in the form of voltage. So, the signal here it is voltage, and the trans-conductance amplifier, it is also expecting input as voltage. So, they are consistent, and here the output of the trans-conductance amplifier, it is current, and I do have current amplifier. So, the current amplifier is expecting signal in the form of current. So, then there is no problem, and here we do have the signal coming from the current amplifier is of course, in current form, and then we do have the trans-impedance amplifier, which is of course producing the signal in the form of voltage. So, we do have here it is the signal, it is in the form of voltage, finally it is coming to the voltage, and it is going through different other modes of signals. So, that is why we can we may have a chain of amplifiers having each of the stages are of different types of amplifiers. Now, the natural question is that in case if the signal here and expected signal to the next stage, if they are not consistent, then what do you do? Luckily, each of the stages they do have their own practical output impedance or output conductance element, and you can nicely convert the output port model into appropriate model, namely Thevenin equivalent model you can convert into Norton equivalent and vice versa. So, those kind of after seeing what kind of amplifier it is cascaded to, you may have to adopt those things, but as a individual building blocks we do have this kind of 4 basic models. They are sufficient, and each of those models are having primarily 3 elements. I think let us summarize what we have discussed in the today's class. Primarily we have discussed about the linearization of amplifier, namely simple amplifier, and that results to the models of the amplifier. Depending on the signal type, we do have voltage amplifier, we do have current amplifier, trans-conductance amplifier and trans-impedance amplifier. And each of these types of amplifiers, what we are doing is we are simplifying the circuit into one equivalent circuit. The circuit is simple enough, it is simple enough, but it is also it is sufficient to capture whatever the information we are looking for. Namely, it represents the input to output signal relationship, whether it is voltage gain or current gain or trans-conductance and trans-impedance, particularly in unloaded condition. And also it is having the other two parameters, namely output resistance and input resistance, or maybe output conductance and so on, to capture the loading effect when you consider practical circuit. So, I think these models are pretty handy whenever we will be having fairly more complex circuit. What we will be doing is that these basic models we have to keep in mind. So, whenever we do have one amplifier, we must always try to translate this circuit in this form, namely whenever we do have this amplifier, we need to say, suppose this is voltage amplifier, then how do we find the basic three elements, namely the open loop voltage gain, output resistance and input resistance. So, that will be the exercise we will be performing whenever we will be going to the actual circuit and converting that into the corresponding model. I think that is all I do have. Thank you for listening.